Hi everyone, this is the first video for day 2, week 3. So far we looked at trigonometric equations that were solved using techniques from Math 103 like factoring. And now we're going to throw a new thing into the mix, which is using identities and then reducing it to unknown form. For example, if you want to solve this right in the form that it is, you're not able to substitute any one of them because they are different things. However, we do know that cosine squared is 1 minus sine squared theta, which would mean that I can rewrite this in this particular form, giving me 1 plus sine theta is 2 minus 2 sine squared theta. And then collecting all the like terms, I get 2 sine squared theta plus sine theta minus 1 equals 0, which is now reduced to a previous problem that can be solved by splitting the middle term, in which case I get 2 sine theta plus 1 minus 1 sine theta plus 1 equals 0, giving me 2 sine theta minus 1 times sine theta plus 1 equals 0, yielding two solutions. Sine theta is 1/2 and sine theta is -1, both of which are going to have two solutions each for the general case. So sometimes when you are solving and they are not the same ratios, you want to sort of think of any identity that you can use to convert them into one variable. For example, here I'm going to use the fact that sine 2 theta is 2 sine theta cosine theta, and observe that I can factor out cosine theta by grouping them, which gives me cosine theta is 0 or sine theta is 1/2. This we know has a solution pi over 2 plus 2k pi or 2 pi k, and this is going to have two other general solutions. So there are going to be three general solutions in this case. Now let's look at some trig. We solved a problem similar to this, the only difference being that we had a cosine squared, which made things easier. However, if I have cosine theta plus 1 equals sine theta, and this time around I'm not finding a general solution, what I can do is I can square both sides to create artificially sine squared and cosine squared terms. When I do that, I get cosine squared plus 1 plus 2 cosine theta equals sine squared. Now I already have two things with cosine here, so I'm going to replace this by 1 minus cosine squared, which gives me 2 cosine squared theta plus 2 cosine theta equals 0. Factoring out 2 cosine theta, I get cosine theta plus 1 equals 0, giving me cosine theta is 0 and cosine theta is -1. This happens at pi over 2 and 3 pi over 2, and this happens at exactly pi. So in this case we are not reporting the general solution because it says to find the solution in this particular range. Now when we are solving equations, not just trigonometric equation but any equation, what does it mean graphically? For example, solving x minus 4 equals 0, algebraically it gives me x equals 4. This means the value of x for which this statement is true is 4. Graphically, I can plot these two functions, y equals x and y equals 4, and ask, when is this true? And this is true exactly at the point of intersection of these two functions. Right? Because solving this is basically solving when is x equal to 4. So that's a general way of thinking about solving. Another point of view is that Say you have two functions, f of x and g of x, and you want to find, so say these are the graphs of the function, you want to find exactly where these functions meet up. What this means is you are trying to solve this equation, fx equals gx, but if you subtract gx, then that's the same as fx minus gx equals 0. So essentially when you're finding points of intersection, you're finding solution to the equation fx minus gx equals 0. For example, finding points of intersection of these means you're setting f of x equals g of x, or you're saying 3 cosine x plus 1 equals cosine x minus 1. But I can subtract both of these terms on both sides to get 2 cosine x plus 2 equals 0, which gives me 2 times cosine x plus 1 equals 0. 2 cannot equal 0, so this gives me cosine x equals negative 1, which has the general solution pi plus 2k pi. Let's say you have to find the points of intersection between sine x and cosine x. Now you can also use some knowledge or some facts that we have already established. For example, I can write this as sine x minus cosine x equals 0. So there's a bunch of ways in which I can solve this. I can square both sides to get sine squared equals cosine squared. Then I get sine squared is 1 minus sine squared. So I get 2 sine squared minus 1 is 0, and I go ahead and solve. Another way is, we learned that a combination of sine and cosine can be written as a single sine function. To do that, I multiply by root 2 and I divide by root 2. Then this becomes sine of a minus b. Pi over 4. So this reduces to, when is sine of x minus pi over 4 equals 0, and that gives me x minus pi over 4 is 0, or in general x minus pi over 4 is 2k pi. So those are alternate strategies that you can use. Find all solutions to 2 sine 3 theta minus 1 equals 0. Now there is a triple angle formula which gives you a cubic equation. You could go ahead and use that, but a simpler way to do this would be to say 2 sine 3 theta is 1. So sine 3 theta is 1/2. So 3 theta is going to be sine inverse of 1/2, which has two solutions. It's pi over 6, and the other one is in second quadrant, so it's pi minus pi over 6, which is 5 pi over 6. So the general solution would be that 3 theta equals pi over 6 plus 2k pi, or 3 theta equals 5 pi over 6 plus 2k pi. But what you're trying to find is theta. So this means dividing both sides by 3, you get pi over 18 plus 2k pi over 3, or you get 5 pi over 18 plus 2k pi over 3. Now you could use a cubic equation and solve, but that's going to be way more complicated. It will be easier for you to find 3 theta and then just divide by 3 to find theta. I guess we can wrap up today's content in one video, so I'm just going to continue. Similarly, you can have half angle situations where also you're going to use the same tactic. So theta over 2 is going to be tan inverse of 1 over root 3, which is I believe is pi over 3. So in general this would be plus k pi, so theta would be, one of them would be 2 pi over 3 plus 2k pi, and then the other tangent is here, so that would be pi plus pi over 3 is 4 pi over 3 times 2 gives you 8 pi over 3 plus 2k pi. So basically, even if you have half angles, double angles, and triple angles, you can just use the method to find the value for theta directly. Here's an application problem. A projectile, meaning anything that's fired from the surface like that, it follows a parabolic path. If it is fired with a velocity v0 at an angle theta with the horizontal, then the range, which is how far it goes on the ground, is given by this particular function, and it returns the answer as in feet. If v0 is 2200 feet per second, what is the angle in degrees that should be chosen for the projectile to hit a target on the ground 5000 feet away? So what you're given is the range and v0. So you have that 5000 equals 2200 squared sine 2 theta over 32. Cross multiplying gives you that sine 2 theta is 32 times 5000 over 2200 squared. And that gives you 2 theta as being equal to sine inverse of whatever that comes out to. Let's see what it is. 32 times 5000 divided by 2200 divided by 2200. Sine inverse of that value. My setting is in radian, so I get 2 theta equals 0.33033 1 radian. So theta is going to be half of that, which is 0.0165 radians. And if I want to convert this into degrees, I multiply it by 180 and divide by pi. Which is a very small value. So that brings us to the end of solving trigonometric equations using tools from Math 103. Next, day 3 video is gonna focus on an application of trigonometry stuff we've learned in something called polar coordinate system. That's it for today.